Hey, welcome back to my shop. Today we're going to talk about a couple ways to remotely control your dust collection system, whether it be a real dust collector or just a wet dry vac. Well, before we get started, I want to remind current and new subscribers that I don't put out videos on a regular basis, just when I think I have something to share, like I do today. And if you're not a subscriber, I invite you to subscribe, and don't forget to click on the bell icon so you get notifications when I do produce a new video. The first way we're going to talk about is using a commercially available transmitter and receiver. The second way is going to be building a circuit by John Heisz. It's a load sensing circuit, and the circuit will automatically turn on your dust collector when you energize the power tool. In my case, we're going to work with a miter saw. John's circuit is really easy to build. However, I made a couple changes. The most important one is letting you use his circuit with two different electrical circuits. So that way you can have your power tool running off one circuit breaker and your dust collection running off another circuit breaker. It's going to be kind of a longish video. It's oriented toward those that don't know much about working with house wiring or electronics. I'm going to take you and go into every detail, including teach you how to solder and where to buy all the parts, even an inexpensive soldering iron. If you know what you're doing, you're going to be bored to tears with this video. You may want to just go to John's website, which is ibuildit.ca. He's in Canada. Then click on Projects, Electronics and Audio, and if you scroll down, you'll find Making an Automatic Load Sensing Circuit. You should be able to build it just from the circuit, but if you want to find out about the changes that I make, you may want to watch my video. Okay, so what I'm currently using is a Westech transmitter and receiver. This is your switch, has on-off buttons. You plug your dust collection into the outlet. The male head goes into the circuit on which you want the dust collection to run. When you press the switch, it goes on. But I'm getting lazy in my old age. What I really want is to hit the power tool and have the dust collection go on. So that's what we're going to do today. Here's the basic plan. This represents the miter saw, and that's the outlet in the wall. So your load sensing circuit is going to plug in between the outlet and the saw. In the circuit that I'm using, the load sensing circuit operates a relay. And in the circuit I saw on the internet, we'll talk about more of that later, the relay was incorporated into the load sensing box. It was all one unit, and that plugged into the outlet. What I'm going to do in our plan is enable us to use a separate circuit for the vac. And so the relay will be separated by physical space, and I have low voltage wire going from the load sensing circuit to the relay box. So the relay box fits between the vac and the outlet on the wall. So when the relay is energized, it actually closes the contacts in the relay. It acts just like a switch, and it turns on the dry vac, the wet dry vac. This is a schematic of the circuit we're going to build. It really has very few components. These four diodes are in one casing that's called a bridge rectifier. We have a transformer, another diode, a capacitor, and a Zener diode. And then the relay. So it's really 1, 2, 3, 4, 5, just 6 simple components to make this work. It's really a stroke of genius on John's part to create this. An interesting aspect of this is the transformer. You'll see it's rated at 120 volts and 6 volts. Normally this transformer converts 120 volts AC into 6 volts AC. But it's used backwards in the circuit. The flow is from left to right. So what this side of the transformer does, it senses a voltage drop across these diodes. And that's only 1.4 volts. So we're picking up 1.4 volts. And because normally a transformer reduces voltage, this one anyway, it goes down. If you hook it up backwards, it's going to boost the voltage. So we put 1.4 volts in here, and we're getting about 15 volts on this side. And that gives us something to work with, because the relay requires 12 volts. So this is quite clever, using this backwards and using the bridge rectifier to give us a voltage drop as an input for the transformer. To build the circuit, you're going to need certain equipment, certain tools and parts, and I'm going to tell you exactly what, where, and how to buy it. To start off, it's going to require a little bit of soldering, so you don't want to invest a lot of money in soldering iron if you don't do this regularly. But you can buy a nice soldering kit, including solder, for 10 bucks on Amazon. Let me show you everything I'm going to tell you to buy. I'm going to give you the ASIN number. Every product in Amazon has a unique number like this. So if you search for that number, the product comes right up. So for the soldering iron, it's right there. You're also going to need like crimp connectors and things. So you might want to watch the video and kind of make a list of what you need, and then get your parts together, then watch the video again and build it. But let's go into some of the other specifics you'll need. The relay, there's the ASIN number. This is about $7.50. The bridge rectifier. And there's the pin diagram and a picture of what it looks like on Amazon. This is $6.81, and you get 2 of them. Next is the transformer. You remember in the schematic it was a 6-volt transformer, 120 volt to 6 volt. What I'm using is a 120 volt to 12 volt center tapped. And what that means is it has 3 lugs, and if you measure from the outside lugs, you get 12 volts, and from a center lug to either one of the outside lugs, you get 6.3 volts. The advantage, well, I happen to have that, but it worked well because I could use whatever voltage tap that gave me the best voltage on the outside, on the output. So that worked out well for me, and that's what I'm going to recommend here is a center tap transformer. There's the ASIN number. It's about $14. Looks like that. It's got 2 lugs for the input, where the 120 volts would normally go, and 3 lugs on the outside. And remember, we're using it backwards. So the outside for us is the input. Outside, I mean output. And then you got the 3 little components that go on the right side of the transformer as relative to the schematic. The first one is a diode. And there's the ASI number. You get 5 pieces for $3.39. And those diodes look like that. Next is the capacitor. It's hard to see on the paper. There's 2 leads coming out. Here's the ASIN number. And you get 10 pieces for $5.88. And finally, the Zener diode is 20 pieces for $5.85, and there's the ASIN number. And they're little tiny things, look like that. John actually calls for a 10 volt Zener diode. I used one, I burned it up, I think because the rating was too low. So I had a 12 volt, so I used that. 12 volt is really what you want. The Zener diode corresponds to the maximum voltage that's going to come out on the right side of the transformer. And the relay is rated for 12 volts, so it makes perfectly good sense to use the 12 volt Zener diode there. Now the next thing is going to be some of that wire, the low voltage wire. I'm using zip cord. Zip cord is like lamp cord. It's got 2 wires stuck together and you can rip them apart. One's black, one's red in this case, and you can use 20 or 22 gauge lamp cord. Here's a 66 foot piece. There's the number. It's number 20 gauge is 679. I'm using 22 gauge just because I have it. And there's a black and white picture. You get a coil of wire. Okay, and I was going to talk a little bit about the wattage draw or the amperage draw of the equipment. My miter saw is a DeWalt DW705. It's quite old. It's over 20 years old. The factory spec is a 15 amp motor. But I have a watt meter, and the startup current when you first turn it on is 32.5 amps. Now you're going to ask, how does that work on a 20 amp circuit? Basically, the circuit breaker, modern circuit breaker, does not turn off as soon as it senses an overcurrent. It has a time delay. So it allows for that initial rush current of a motor. All motors do that. They have a high initial rush current, then it settles down into a running current. The running current on the saw, no load, is 8.2 amps. When I cut a piece of 3/4 inch oak, it went up to 13 amps. So that's the numbers that I need to work with. So the parts that I use need to be rated to handle that kind of current load, not the 32 amps. My wet dry vac, the Rigid WD1680A, has a factory spec of 12 amps for the motor. The startup current for that is 25.8 amps. And the running current is 9.6. So it gives you, again, an idea what we're dealing with. You don't want to use anything less than number 14 wire. To build this, you're going to need some line cords or power cords, these kinds of things. And the best way I found to acquire these is to buy some small extension cords and cut them in half. Amazon has some very reasonably priced cords. I'll put it up on the screen. And if you just want the male side, you could buy from Harbor Freight the 4-outlet power strip and just cut the cord off of that. That's $3.99. I found one for $2.99. And that's a really nice way to get these. These are 14 gauge, just exactly the size you need. You're also going to need some short pieces of the wire that's inside here for little short connectors inside the boxes. And the best thing to do is just take this, cut off what you need, strip it, and pull out the wire and use that. And when it comes time, I'll show you what we're doing with that. So it's time to get started. Let's build the relay box first. Okay, I've got what you need laid out for the relay box. The relay box is going to have a low voltage input that's going to turn on the relay, and the relay is going to, in effect, be a switch and turn on power to the receptacle. We're going to use this switch as the bypass. Now this is a 3-gang electrical box. I'm an electrician, so this is, I've got this stuff. This is some used parts, and it's easy for me. You don't have to do it this way. You could choose to use a 2-gang box with just a switch in the relay, and instead of using a receptacle, you can use the female end of one of the extension cords that you cut in half and wire that in. And it's going to be very similar to what we're doing. You probably can figure it out, because you're going to have instead of screws for the wires, you're going to have a black wire for the hot, and a white wire for the neutral, and a green wire for the ground. I should point out, on the receptacle, there's 2 different size slots. The small slot is always the hot. That's where the black wire goes. The larger slot is the neutral. And if you look on the receptacle, the neutral is on the same side as the ground. That's standard. So the first thing we want to do is, I want the relay mounted in the box in such a way that I could tilt it up to make the connections, and then after I make all the connections to it, I could turn it down and fold it in. So I kind of have to figure out where to make a hole. I'm going to use, to show you this is the relay, I'm going to use these 2 tabs to mount the relay to the side of the electrical box. These 2 are the low voltage tabs that go right to the coil. it's kind of cool that you can see inside here. You know exactly where all the connections go. So these two energize the coil, and it says right on it, DC 12 volts. This tab and this tab is your common. It's connected to that white wire. And these two are connected to the switch, the part that goes up and down. This tab is well, that's not important. Anyway, we're going to use these two tabs, number 6 and number 4, just because it's toward the switch and the receptacle, and it'll be easier to use. Okay, so I'm gonna figure out where this hole is gonna go. I'm gonna make that, and then I'll come back. Okay, I've got half the relay mounted. These tabs will take a number 4 or number 6 screw. 6 is a little tight. I'm using number 4. Actually, I'm using hardware that is left over from when I used to build electronic kits in the early 1970s. So these are like 50 years old. Wow. Anyway, so I've got one screw in. I had to grind off the little raised part on the box. It's a 1/8 inch bit. Made a nice hole for that. And the nuts have a captive lock washer on it, which is very convenient. So it makes it so when you tighten the nut, you can just turn the screw and it holds the nut in place without having to hold it on the inside. Okay, so I think the next thing we're going to do is make the little jumper wires that will go from the various parts in the box. Okay, here's a view of the pictorial that I showed earlier. And I've got the crimp connectors lined up where they're going to go, and the wire nut right there, so you can see it. So I've got the wires numbered. So this first one that's going to go from the receptacle to the relay is wire number 1, and that's going to be 7 inches long. And it's going to have a spade lug on one side and this quick disconnect lug on the other. So we're going to need 4 wires for interconnections in the box. So we're going to have to use some white wire as well. So we're going to use black and white from this. The green is always ground. I don't want to use that. But the white's okay to use. So I'm going to cut off 12 inches off my extension cord and then strip it and make the connectors. Let's do that. The easiest way to cut this cord, I'm going to measure 12 inches right here, is if you have alignment pliers. If you don't have that, if you've got a long nose pliers that has a cutting part, that might work. And if that doesn't work, maybe even the wire stripper part. Let's try that, because you might have a wire stripper. The other thing I was going to do is trim the insulation with a knife and then cut each individual wire separately. But let's see if this works. This is not too bad. The wire in these line cords is kind of soft. It's stranded wire. So it should cut fairly easily. Okay. Now I'm going to take a knife. I'm going to just let a little bit of the knife be exposed and go down the insulation. Remember, I'm making the little short wires for the interconnections in the box. Try not to go too deep because I really don't want to damage the wire. You can hear it snap because I didn't cut all the way through. Well, it's not snapping now. Okay, I think once you get a little bit out, you could probably... Alright, so we're trying to get the wire out of here. And sometimes you can just pull it through and it'll tear the insulation open where I slid it. But if you don't slice it deep enough, it won't. Okay. We're not going to use the green. That's too confusing. We can use the white, and if you're real fussy, you can put a piece of black tape on it so you know it's black, because all the wires in the box are carrying the hot side of the current, so they should be black. The white wire is neutral, and it's not really a hot wire until current is passing through the circuit. Okay, let's start by making one of these 7 inches. 7, I'm going to strip the end. This is wire number 1. When you're doing stranded, you always want to twist the end after you strip the insulation off. If you don't have a wire stripper, you could take a knife and just kind of go into it little by little and then break it off. Okay, so let's put one of these on. That's good and tight. And when on these could actually be blue. Blue would work with number 14 wire, but I don't have any blue ones like this. So this is actually for a larger size wire, but it works. It crimps on tight enough. So with this particular crimper, it's not squeezing the blue tight enough. So what I'll do is squeeze it with the red part, the red side, and it'll make it a little tighter. Okay. Now it's good and tight. What you don't want to do is strip a wire This is going to be wire number 2, which is going to go from the receptacle to the switch. Now, if you just take this wire and make a hook in it and try to put it around the screw, it tends to spread the strands out and push it away from the screw. You can see that it's coming out around there. And it's not really a good connection. You don't have all the copper under the screw. This is not a good way to do it. I meant to show you this before. A better way, if you don't have the connectors that I'm using, if you really want to put it under the screw, is to tin the end of the wire. Tinning is when you just add some solder. Make sure your soldering iron is on. Just add some solder to the tip and then touch it to the wire. And if you can coat that entire wire and get the solder to actually melt and coat all the strands like that. So that looks pretty good. Let's see if you can see it. Maybe against the blue. Now, you could take along those pliers. Now it's pretty stiff. It's kind of hard to bend. You could do that. And now when you tighten the screw, it all stays together and it makes a good connection. So that's the way to do it if you don't have the connectors that I'm using. So I'm working on the hot side, and actually my drawing shows these reversed, but it doesn't matter. But I like using these. These make, I think, the best connection. Get it under there, and it holds it really well. We're going to bring the line cord into the box. I'm going to use... Okay. And you want to strip about that much off. It's easier to strip this, or as I say, it's harder to push the wires through if they're already stripped. So I tend to strip it after I push it into the box. I'm going to pull the wire back through. It's got a plastic retaining clip that holds the wire in. So you have to kind of bend that up and then push or pull the wire back through. Strip all the wires. Okay, I've got those stripped, and now I'm going to put on the connectors. Connectors are on. Put the white under the screw on the same side as the ground. It's also the side with the longer slot, either screw, and that'll make the neutral connection. Don't forget to make these things tight. And then the ground connection is going to go here. That's the ground screw. The ground screw electrically is connected to the frame of the receptacle and to the round hole. I'm not going to go into a big explanation of what the ground does. It's just really for safety. Okay. Now, the black wire is going to go to the relay. So this could be installed now into the box. So one of these goes to the switch. This is wire number 2, goes from the receptacle to the switch, so I'm going to strip it. Power wire is designed to go under the wire nut. So that's going to join the wire from the other side of the switch. We'll put this one here. Again, this is wire number 2. It's going from the receptacle to the switch. Now we need to go from the switch to a wire that's with nothing on the end. So that wire could be about 6 inches long. So I'll reiterate that the switch bypasses the relay. Both of these are switches. This is a mechanical switch. You operate with your fingers. This is an electrical switch. It's operated by an electric current, in this case coming from the load sensing circuit. So we have our 2 wires here. Do not concern yourself with the ground screw on the switch. What we should have done before was put in the low voltage wire, but that's not going to be a problem. We're going to do that now. So this is the zip cord, also called lamp cord. It's also called speaker wire. This is 20 gauge or 22 gauge. I'm going to drill a hole and bring this down to the bottom, and then it's going to come up and connect to these 2 terminals on the relay. Okay, I've drilled the hole for the wire. I'm going to push it through. Grab it. I don't know how long this is. It doesn't matter. If it's too long later on, you can cut it. What you do want to do is tie a knot in the wire, somewhere like that. And that will be the strain relief. When I pull this back through, after making the connections, it'll stop there, and any tension on the wire it'll be prevented from exerting tension on the terminals. So we're going to connect a couple of these. Oh, these are going to be too big for that wire. Let's see if I have some red ones. Okay, yes I do. These are some red quick disconnects that'll fit on the lugs of the relay. I've got one on, but I want to show you sometimes the wire is a little thin, especially when you strip it, you cut some strands off. What you could do is fold it over and squeeze it together. Get that tip squeeze pretty good, and then see if it goes in. See, that goes in much tighter. Okay, that's gonna go, doesn't matter which one goes on which right now. And I'm gonna bend these up so they don't hit the side. This one I'm gonna bend down so they don't hit the side of the box. Now we need a short wire. This was wire number 1 coming from the receptacle, and it's going to go, I'm going to stick it here. Remember, these sets of tabs are identical. You can use one set. Originally I thought I was going to use this set because I thought it was going to be closer, but now I see this is going to be easier to use. So the wire from the receptacle is going to go to one of these tabs. This is tab number 5. And now we're going to make a wire to go from tab number 6 that'll join the power cord, and there should be another wire in here from the switch, this one. So this wire only needs to be about that long. Okay, so I made this wire and I put it on terminal 3. This is 1, 3, and 5. Now I could push this down after I loosen my screw a little bit. We'll see how well it fits. Okay, so I'm just going to bend these toward the switch a little bit so it fits flat against the box here. Then I can put in my other screw. Okay, my relay is mounted. I'm double checking my wires. Nothing shorted out. Remember, this is line voltage, so you want to make sure everything is where it should be. Twist these all together. Use the wire nut. Tuck that in. I could screw down the switch. Let's strip this end. Now we're going to test it. The easy way to test it is to grab a 9-volt battery and touch the wires onto the terminals. I think you can hear it click. You might be able to see it click. Okay, now let's do a live test. All right, for the live test, I'm going to plug this in. Now, for the first time, I would do it real quick just to make sure nothing's shorted out. If you have a short, if you have something that's wrong, at least it'll minimize the damage or how scared it'll make you. Okay, it worked. So I don't have an outlet handy right where I can record this, so I have a little extension cord here. Switch is off. I'm going to use this circuit tester as my shop vac. And if I turn the switch, those lights should come on. Oh, good. And the 2 yellow ones are what's supposed to come on. And if I touch this to the battery, it should also come on. So it looks like we're good. So once the load sensing circuit sends a signal to these wires, the shop vac is going to come on. In fact, I happen to have a shop vac here. Let me hook that up. Okay, here's my shop vac cord. I have the switch on the shop vac on. That's important. Now it should go on. That's good. And from the relay. We are golden. To get a plate for this, it's really hard to find a wall plate that's blank on the end and with this combination of devices. They sell a sectional plate. I know Lowe's and Home Depot both carry them. So it comes in separate pieces and you snap them together and you can make any configuration you want. It's about $2 a section. Kind of pricey. Or you can make your own, I guess. Anyway, the relay part of this is good to go. Okay, it's time to talk about the load sensing side of it. So as you can see, these are really all the parts that are required for the load sensing circuit. Let's talk about each one. So the first one on the paper you can see is the bridge rectifier. So that's this part here. That's the diagram for it, which tells you which pins are which. And if you look at the real one, you'll see that all the pins, 3 pins, are in the same direction. Let's do it like this. These 3 pins go horizontal and this one goes vertical. And if you look at the picture, the vertical pin is the positive. The opposite pin is the negative, and these 2 pins have a little tilde sign. That means AC. So these 2 would normally, when you use this as a rectifier, that would be the AC connection, and the output would be positive and negative DC. That's the purpose of a rectifier, to change AC to DC. But this circuit is very, very clever. And John, who figured this out, or I guess he figured it out, I think is a genius for figuring this out. I would have never thought of using a rectifier as a load for sensing the circuit. Anyway, so what we're doing, we're taking the positive and the negative and we're connecting those together. And we're just using the 2 AC terminals. Next is the transformer. And as I explained earlier, this is really a 120 to 12 volt transformer. The reason it has 3 lugs on this side, because there's 12 volts between the 2 outer lugs and 6 volts, or 6.3 to be exact, between the center lug and either of the outside lugs. So if you measure between these 2, if this was connected to the line, if you measure between these 2, you get 6.3. Between these 2, you get 6.3. But when you go on the outside, you get 12 volts. 12.6 to be exact. So we're using it backwards. Normally that's the input and that's the output. We're putting in a very, very low voltage and we're trying to boost it to a workable voltage. Okay, next is a diode. It's going to look like that. It's tiny and it's got a band on one side indicating the positive end. There's a positive and negative to the diode. Next is the electrolytic capacitor. And yours is going to look like this. Mine was a used one, so I extended the leads, just so you know what it looks like. And it could be black, it doesn't have to be brown, and one lead will have an indication for a negative. Let's see. So that's the negative lead, and it probably will be shorter than the positive lead. And I don't know if you could see it. Nah, probably not. It's 100 microfarads at 50 volts. A 35 volt one will probably work as well. Next is a Zener diode. It's kind of like a regular diode, but it works a little differently. A Zener diode limits the voltage going across it. And I already mentioned the 20 gauge wire. I'm using 22 because I just happen to have it. So we're going to build this on the bench. We're not going to talk about boxes yet, what kind of container, because there's all kinds of things you can do for that. So the first thing we're going to do is teach you how to solder. Now, going back to the rectifier, I've already mounted mine on a heatsink. If you look at John's original, there we go. If you look at John's original video, he mounted his on a piece of aluminum, and he just had a vertical piece of aluminum, and he bent the bottom over. Then he made 2 holes and he mounted it. You could do that too. I happen to have this heatsink that's made for transistors. And I just drilled a larger hole, put this on it, and I've got a couple screws on the bottom where once I put it in my box, I can screw it up from the bottom and that'll hold the vertical. So, time to learn how to solder. And we're going to start with the transformer. It's very low current coming into the transformer. So we're just going to use a piece of the zip wire. That's that 20 gauge wire that we talked about. I've already separated one end. Now I'm going to strip it. Now I've got several wire strippers. I'm going to use one of these. In fact, I'll strip one with the wire stripper. You got to be careful try not to cut any of the copper. Always twist stranded wire after you strip it. Then the other one, if you don't have a wire stripper, it could be done with a knife if you're relatively careful. Just kind of cut in all around gently and pull it off with your thumb. Okay, and I'm working around the camera, so it's a little awkward for me. So what I'm going to do is I have a long nose pliers, which is nice. When you solder, whenever possible, you want to make a physical connection as well as a solder connection, which is the actual electrical connection. So you do that, you push the wire through the lug. In fact, you don't even need the long nose pliers. And just bend it over. Do that to both. Okay, so plug your soldering iron in, get it warmed up. The solder, first touch the solder to the tip of the soldering iron, you'll see it melts, and then you know your soldering iron is hot enough. It also helps with the heat transfer, so you want to do that anyway. Get some solder in there, touch it to the intersection between the wire and the lug, and if you start touching the lug and the wire, the solder should melt, and when it starts to flow, then it's good. Let's do the black one. Put some solder on the soldering iron, touch it to the connection, to the joint between the two. Start touching the solder onto the wire or the lug. If you're not getting a heat transfer, put some more solder on the soldering iron. And you'll see when it starts to flow. It's real shiny, and it actually flows like a liquid. Then you can pull the soldering iron away, and you've got a good connection. You've got a mechanical connection and a good electrical connection. Sorry for kicking the tripod. On the other end of the wire, I've just stripped it and twisted them together. These are going to go under the wire nuts, and the wires going to the bridge rectifier. Okay, so that's going to be low voltage. It's actually about 1.4 volts that goes into the transformer, very low. Next, we're going to start connecting these components. Okay, with the actual electronic components, they're more heat sensitive. That's why we wanted to practice on the wires first. If you can do that the way I did, with just minimal amount of heat, not excessively heating the joint, if you could do that, you've got soldering down. I mean, if you need to practice a little bit, take some more of your zip wire and just try melting some solder onto the tips, just to get a better feel for how to solder and what it feels like when the solder is flowing. Okay, on the outside, we're going to start with the diode, the regular diode. By the way, a diode changes AC to DC, similar to this rectifier. The rectifier is just 4 real big diodes inside a container. So it's exactly the same, just 4 of these in one of those, and then it's hooked electrically in a way, so it gives you full wave rectification. I won't even go into that. Never mind. Anyway, this does change AC to DC. So you want to kind of do what we do with the wire. Long nose pliers is handy here, but I'm going to assume you don't have one. Just take the lead, maybe like in the center, make a little U, put it through the loop. The band, the indicating band for the positive side should face this way, face to the right. Let's see if we're in camera. Where'd it go? Yeah, so the band is toward my thumb. And then to bend it down. And if you can squeeze it down so it kind of stays sticking out, that would help you solder. In fact, let's see if I can do it with my fingers. More or less. There. Well, that's close enough. Because once you solder it, you could bend it so it sticks out or down or up, whatever you want. Now, you're going to do the same thing, but I'm not going to use this diode. I love recycling and using older parts, so I've got this used one that I'm not even going to crimp. I'm going to fill the hole with solder in the lug. I'll turn it so you can see what I'm doing. Now you're going to crimp it and solder like I did the wires, but I'm going to put some solder in the hole there. It's almost completely filled. And then I'm going to grab my diode, and I'm grabbing it by the end with the band, and I'm going to heat the solder and push this through and see if I could get the solder to build around it. I blow on it to let it cool faster, and there we go. So you're going to have that. You would have pinched the wire around the lug, because that'll make it a lot easier for you to solder. Next, we're going to hook up the capacitor. Now, this is going to be the positive side. Positive's coming out. The capacitor goes between this lug and this end of the diode. Now, because this is positive, you want the positive end of the capacitor hooked to that, and the negative end hooked to there. So I'm going to hook up the negative first, because that'll hold it. So I'm going to do the same thing. I'm going to mount my capacitor. I'm eventually going to bend it down. So I'm going to start by making a little U in it, putting it through the lug, and crimping it. That's what I was trying to show you to do with the diode. It is easier if you have little pliers or long nose pliers. Makes life simple. Okay, then just like we did with the wire, put a little solder on the soldering iron, touch the lug and the wire, get the solder to flow, pull it away, and we've got a great solder joint. This wire is very thin, easily bends down, so I'm going to go ahead and bend it down. Bring that up. And if you have a wire cutter, it'd be great to cut that wire. If you don't have a wire cutter, let's see if a scissors will work. This wire is kind of thin. Use a scissors. Okay, and if you can't do that, just bend it down along there. It'll be fine. This is a very non-critical circuit. Okay, so I think I'm going to bend this up. And then I'm going to wrap this lead around like that and solder that. The Zener diode is going to go right across the capacitor. So it's also going to connect to that post and connect around that lead. Okay, you can actually, well, we don't want to get fancy. Let's just put a dab of solder on there just to kind of hold it. Double check that you've got the band. There we go. Double check you got the band away from the transformer. There's the little gray band. Okay, now I'm going to clip the excess wire. Now your Zener diode is going to have two long leads. So my lug still has a hole in it. So if I had a long lead Zener diode, I could stick it inside there and bend it around. This is a little short. I could add a lead to this. I'll do that. I'm going to take that off camera for a second. Okay, we're back. Now I've got one that looks more like what you have. Two reasonably long leads. So I put it through the hole. Now if you don't have a hole, let's say your lug is filled with solder, then make a U in it and just stick it around the wire. And you could just bend it around the wire kind of tightly. Up on top. Just do something to make it stay up on top so you can solder, because you could bend it afterwards. And you could trim it afterwards. So just a drop of solder. You don't need a lot. And there's my lead that I'm going to cut. I'm going to use the wire cutter, but the scissors works. Bend that out a little bit. And bend it around so it's kind of looped. Now I don't have to pinch it tight. It's just looped around to position it. Because after this we got two more wires, and that's the output. I'm going to hook up more red and black wires like this. The red one to the positive side, and the black one will be our negative. So positive and negative coming out, because this is DC. On DC, positive and negative matters. On AC, it doesn't. These could be the same color wires here. But on the output, it matters. In our circuit, this goes to the relay. It just so happens that with the relay, it doesn't matter positive and negative. You can hook them up in either direction. But if you were building a real circuit, then, well, this is a real circuit. If you're building something else, it could matter. All right, so I'm cutting off the excess. Okay, so I've got, on the positive side, let's take a look at this. From the lug, we go right to the diode. To the outside of the diode, to the positive side of the diode, we have both the capacitor and the Zener diode connected. On the other side, on the other lug, we have the negative of the Zener diode and the negative of the capacitor. So this is actually the negative or ground side of our DC circuit. Okay, I just grabbed another piece of zip wire, just a short piece. Separate them. I'm going to use my wire stripper to strip them. Twist them together. Okay, so this is going to go like this. Now here's a good time that we're going to tin them, because when you bend stranded wire, it doesn't always stay exactly where you put it because it's so soft. But if you tin it, which is like this, I'm going to see if you're in the frame. Down. Tin it, then it becomes stiffer. So when I bend it and crimp it over, it'll stay. So soldering the same way, put some solder on the tip, put the tip on the wire, and then touch the wire with the solder. And you see it flows nice. And it's nice and silver. The whole length of the exposed copper is silver now, the color of the solder. So now when I bend it, it stays. It doesn't easily go back. So that'll allow me, what I'm going to do, the negative has to go on the lug, just the way that the Zener diode and the capacitor did. And the positive goes on the positive end of the diode. Everything in camera? Okay, so first I'm going to do is Just make a tight loop. And if you have little pliers or something, great. If you can squeeze with your fingers, great. It's best if you had one of those pliers. Okay, I'm going to solder this first, because that'll help hold the whole wire. Okay. That's nice and tight. I've got a good connection there. So this can go up here. Form a loop where I want it. Right about there. And then squeeze it. I'm sorry, it's hard to see what's in the camera. Okay, apply a little solder. Trim it. And that is good. Okay, I'm gonna strip this end. So you remember the relay box has these wires coming out as well. And they basically just get connected with another length of this. So you could either solder those if you really want it to be permanent in your shop, or use small wire nuts. Or even if you have connectors, if you've got some red connectors like this, male and female, if you want to crimp on and then just plug them in on both sides, you could do that. I'm going to use little wire nuts. This is too fancy for me. Okay, so I'm going to test this. Let's go back here, and the way I'm going to test it, let's see, I wonder, you really can't test it the way I'm going to test it. So, okay, we'll skip the testing. But examine your work. Look at the schematic again. If you have to go back in the video and do that. Examine or inspect your solder. Make sure it's all shiny. The hole in the lug does not have to be filled. Just make sure all the solder is shiny, nothing loose. And it looks good. And the same thing with these. The holes are not filled, but the wire is crimped over the lug and then soldered, and they feel secure. And that's 90% of the load sensing circuit. Let's work on the rectifier. Okay, so decide how you're going to mount the rectifier. If you're going to use a piece of aluminum, it gets a little warm. I was testing this before with my 8 amp load, and it does get warm, so the heatsink draws the heat away from the rectifier. With all solid state components, all transistor and diode kinds of things, heat is the enemy. So if you could draw the heat away, that would be better. I don't know how long it would last or if it would burn out if you didn't use a heatsink, but it's probably a good idea. So just a plain flat piece of aluminum will work fine. Like I say, look at John's video for an idea. So once you've got that, make sure you know once it's mounted. Of course, you can tell by the position of the pins. You want the positive and the negative connect together. So make a short piece of wire. I used 14. If you need extra 14 gauge wire, use it. Cut off an extra piece from one of the cords that you're going to have for the line cords. Whether it's the thing from Harbor Freight, the power strip, you're using that cord. Cut off a couple inches of one of the wires. Or another thing you could do is buy an extension cord. Now for the sake of expediency, I'm using the wire stripper. This is 14 gauge extension cord. Now, if you strip it a little bit like that, you can actually use that as a handle and twist the wire and then pull it off, and then finish twisting it. See, makes it twist nice and tight. Okay, so that's the cord that's going to be the line in, because it's got the male head on it. The output, which could be the female end of your extension cord, I've got it hooked into a box, not because I need to, but that's just, I had the box. I didn't have another female head or extension cord that I wanted to cut. So I'm going to use this little box with the cord. I happen to have that box. It's called a sidecar box because it's got this little extra section on here. All right, let's unplug these. These are my lights that I use for the load, for testing. So I've got the box, here's the cord. And it'll probably be easier if I strip a little bit more insulation off here. Now, if you look at the schematic, we're going to have, let's call this, it doesn't matter which one, because these are both the terminals with the tilde, the AC terminals. This one has a little solder on it. We're going to get rid of that. If you're using extension cord, it'll be better than the wire I'm using. It won't be as stiff. This is pretty stiff wire. This is THHN. It's wire that's used for pulling in pipes for electricians. So we're going to have the input. The hot is going to go through the diode, through the rectifier, and to the load side, the side that you're going to plug your load into. This is your hot side. So we're going to twist these together, add one of the wires, might as well be the black one, from the transformer. You could solder it if you want. I'm using a wire nut. I've heard people make fun of us in North America because we use wire nuts. I think the Europeans make fun of us. Wire nuts are an accepted electrical device. You know, it's always used when you're making splices and house wiring. So I don't know what the problem is. I love wire nuts. Okay. The other black, we're not worrying about the white and green right now. The other black is coming on the other side of the rectifier. So in essence, when this first cord is plugged in, the current's going to go through the black wire, down into the rectifier, then out here, and go into the female outlet. So let's twist these together a little bit. Add the second wire from the transformer. And I have another wire nut here. Okay, so that's the path of the current on the hot side. On the neutral side, we're just going to hook these two together. And the grounds also get connected together. Here's the finished load sensing part of the circuit. I decided not to wait for a box, so I went over to Home Depot and I found this one. This is a 6 by 6 by 4 inches deep. It would have been nice if I could have gotten a 6 by 4 by 4 inches deep, but that's what they have. This is 12 bucks. I kind of splurged. Didn't want to spend that much. but it does look nice and neat. It's got 4 mounting tabs. So let me open it up and show you how I put the parts in it. Okay, the cords come in through, these are Romex connectors. For 1/2-inch knockouts. And you can buy a package of 5 of those at Home Depot. And it takes a 7/8 hole. On the left is the heat sink, which is screwed to the bottom. 2 screws and washers. The transformer is mounted to the bottom with 2 screws and washers. And then there's a hole drilled for the low voltage wire for the 12 volts going to the relay. A knot is the strain relief. So everything is good. You can pull on all the cords. Not going to do any damage. It's secure. It's relatively airtight. Probably shouldn't get too much dirt in there. And it makes a neat installation. All right, we're ready for testing. So here's our load sensing circuit. This represents the cord going to what would be the miter saw. I've got it hooked up to some shop lights that draw about 8 amps, so it gives it a good current. You need enough load. The circuit is load sensitive, which means if you only plug the light bulb into the load sensing circuit and turned it on, it wouldn't draw enough current to give the voltage we need through the transformer and to trigger the relay. So it has to be a substantial current. I haven't figured out exactly what you need, but I'm guessing 5, 6, 7 amps, and I've got about 8 amps worth of lights connected to it. So this represents the wire that would go between the load sensing box and the relay box. In my shop, these would be separated by about 15 feet, so there'll be another piece of wire in there. For the shop vac, I've got a light bulb hooked up into the receptacle. So, make sure the power's on, we're good to go. This is the bypass switch, we're going to do that first. When I hit the bypass switch, that should turn on the shop vac, in this case the light. Works great. And I've got a switch over here to turn on the lights, and this would represent the miter saw. So when I hit the switch on the miter saw, shop vac goes on. Again, in this case, the light. So it's working perfectly. All we have to do is install it now. We're back in the garage. Everything's installed. I'm going to show you how I have it. Looks kind of messy, and I don't cut miters on my miter saw too often. Mostly just 90-degree cuts. So this is not in the way. But I'm thinking I could mount that box underneath the workbench and just drill some holes and run the cords under there. So I might do that if that gets in my way. And then on the other side, where the shop vac is, it's under here, and the cord comes up behind the workbench, and I don't have a plate yet for the relay box, but this is the cord from the shop vac. This is the power cord that's plugged into my circuit here that goes to a separate circuit breaker that runs a shop vac. So, let's prove to you that it works. Okay, I've got the camera set up near the shop vac, so you're not going to be able to see it, but you're going to hear it when I run the miter saw. There we go. Works as designed. Well, that's it. I know it was a really long video, over an hour, but I tried to cover everything in as much detail as possible to enable just about anybody to build this. It's really a great thing to have. Again, I want to thank John Heisz for his circuit, his design, and I want to thank anybody who's still with me. Thank you for hanging in there, and thank you for watching, and I'll catch you next time.